All right, we are going to be looking at problem number 2 from the harmonic motion problem set. So we have the steamboat problem. Let's go ahead and read what it says and see how we can model this with a graph. So Mark Twain sat on the deck of a river steamboat as the paddle wheel turned. A point on the paddle blade moved in such a way that its distance from the water's surface was a sinusoidal function of time. So again, we're dealing with something moving in a circle, and we're tracking its vertical positioning. So obviously that vertical positioning is going to, oscillate up and down around a midline. So it makes sense that this is a sinusoidal relationship. When his stopwatch read 4 seconds, it was at its highest point 16 feet. So highest point up here, the paddle was 4 seconds and it was 16 feet above the water. The wheel's diameter is 18 feet. So the distance from the top to the bottom is 18 feet. So that means that down here, we're actually at -2 feet, or 2 feet below the water surface, because we're calling the water surface here. This is actually at 0. All right, so let's go ahead and kind of keep thinking about this. The diameter of the wheel is 18, so that means that our radius here from the midline to the maximum is going to be 9. So 9, the radius of this wheel is our amplitude. So our amplitude is 9. A equals 9. All right. And it completed a revolution every 10 seconds. A revolution every 10 seconds. That is our period. So our period is equal to 10 seconds. All right, so what we're going to be trying to do first is just to create a little sketch of this problem so we can kind of see what's going on. So I'm going to think about scaling along my y-axis. So along my y-axis, I know I need to go up to 16 and down to -2. So 2, 4, 6, 8, 10. Looks like if I just count by 2s, this will go reasonably well. So I need to go down to -2 here. This will be 0. We'll just count this up. Okay, so that's pretty good. That'll be our maximum. We didn't really talk about where this midline will be. So it'll be 9 feet below the maximum, which is actually at 7. So our midline is going to be here at 7. Let's go ahead and draw in a couple guiding lines for our graph. So maximum is up at 16. Midline is here at 7. And the minimum is down at -2. And obviously 0 is the water surface. So maybe that's useful to think about. I'll just draw blue here just to remember that that is the water surface. So once we go below that, the paddle is actually going into the water. All right, so we know that a revolution every 10 seconds. So 10 seconds being our period, that's how long it's going to take to complete a full cycle. And the only point that we do know right now is right here, 4 seconds. At 4 seconds, it'll be at its maximum. So we know, let's just go ahead and make that a point. So let's go ahead and graph that as a point. So we have 1, 2, 3, 4 seconds maximum. That is a data point that we have, 4 seconds, 16 feet. Now, this could be a point that's in our cycle. It could be the start of our cycle. It just sort of depends for us. In general, when we are given a data point, I'm just going to use that as the beginning of my cycle. So in this case, I'm beginning my cycle at a maximum, which tells me to use cosine, right? A cosine curve starts and ends at maximum, right? Cosine curve looks something like this. And then these are our midline points. So when I do this, I know that I'm thinking about a cosine curve. All right, well, it starts at maximum. It's going to end full period away, 10 seconds after this at maximum as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 seconds away, it'll also be at its maximum, which would be 14 seconds and also at 16 feet. Okay, in the middle of that, so exactly in the middle between 10 and 14, we add those together and average them. That's 9 seconds. So at 9 seconds, which I believe is right here, 5, 6, 7, 8, 9. We're going to be down at our minimum value. That's cosine down at the minimum. And from there, we can figure out our quarter point. So between 4 and 9, our another quarter point would be here. It'd be at 5, 6.5 seconds. We're going to be at midline. And at, here's another quarter point at 9, 10, 11.5 seconds will also be at midline. So I've kind of established my graph here. I feel pretty good about it. I can kind of sketch it in and see what's going on with it. So remember, what's going on here is we are tracking a blade moving around it. We're kind of watching that and seeing where it's going and following its distance from the water. So it starts up here at 4 seconds, we're up at the top, and then we're rotating around, and then we hit the midline at, what do we say that was, like 6.5 seconds. Oh, I kind of misplotted that. That should be over here, right? At 6.5. So let me make that adjustment. That's where it should be. Anyway, 6.5 seconds about its midline, and then we go all the way down to its minimum, which we said was here at 9 seconds. This is 9 seconds. And as we're following, it's down the minimum, it's down below the water now. It's in at the very bottom of the wheel down here, -2 feet, I guess, below the water, 2 feet below the water. And then it's on its way back up. Hits that midline again at 9 feet, or 7 feet rather, and then it goes up to the peak again. Full revolution, full cycle there. So here's our graph. We want to go ahead and take this and try to write an equation. We have discovered most of the elements of this, at least most of the things that we're going to need. Our amplitude, so that's A. So we got that. We need to know B, so we need to use this period to figure out B. Remember, there's always this relationship that period equals 2 pi over B. Or if we kind of solve this differently, that B equals 2 pi over the period. So we can also solve it that way. So in this case, B is 2 pi over 10, which is pi over 5. So that is our B value is pi over 5. So that's good. We'll use that. Our C value is how far to the right did we shift this? So we started our cycle here at 4 seconds. So our C value is 4. So that'll be our C value in the equation. And our D value is here, right? What was our midline value or our vertical shift? And so our D is 7, and we shifted up 7. All of those things together, we can use that to write the equation. So I'm going to go ahead and do that kind of in some of the only place left to me here. I'm going to erase some stuff down at the bottom and kind of write it down there. Remember, we're doing a cosine curve, so it's y equals 9 cosine. B value is pi over 5. And then it's x minus c. Our c value is 4. And then our vertical shift was up 7. So there we go. That is our equation for this, this paddle, following this paddle. We're going to go ahead and take that equation and see if we can answer some questions about it on the next slide. So let me move over to the next one. And I'm going to write that equation out again just so that I remember it. Okay, x minus 4 plus 7. There we go. So that was the equation that we had. Remember that in this equation, y represents the distance above the water, and x represents time. So x represents time, and the y represents the distance above the water. Okay. So let's answer these questions. How far above the surface was the point when Mark's stopwatch read 5 seconds? Okay. Pretty easy problem. We're just going to substitute 5 in for x. So I'm going to do that calculation. So I'm going to write out what I'm going to use my calculator to do. You could use Desmos, or you could use a graphing calculator of some sort to do this. But I'm just replacing x with 5. So let me do that. We have 9 cosine pi over 5. 5 minus 4 plus 7. So I'm going to show that. Do make sure your calculator is in radians. Desmos does default to radians, but if it's not, you're going to get a wrong answer here. So we got 14.28 or 14.3. I'll round this and call it 14.3 feet. Remember, this makes sense because we know that at 4 seconds, it was at its peak, and it would be coming down from there. And 5 seconds is pretty close to that. So it's dropping just a little bit below the peak here. So a little bit below 16. And yeah, that kind of makes sense. All right. And then the next one, same process. You know, we just plug in 17. So instead of this 5, we're just going to put a 17 here, and we're going to see what we get there. I'm just going to go ahead and do that. I'll edit my equation in my calculator, or my calculation here in my calculator, change that 5 to a 17, and I got y equals 4.2. 4.2, let's just take a look at this on the graph and just see if that does indeed sort of look like what would make sense to us. 4.2 feet. So I'm going to go back a page here. So at 17 seconds, so this is 15, 16, so 14, 15, 16, 17. So we're looking right here at 17 seconds. So I guess this sort of makes sense. We would be kind of on our way back down somewhere in here, right at 4 feet. Yeah, that kind of makes sense that that's about where we would be on our way back down there. So I didn't sketch that out great, but that does make sense. We were on our way back down there, and yeah, we could sort of use the symmetry of this graph to kind of help us out. So 1, 2 point. We know that midline would be right there, and then right here we'd hit the minimum. So we could just sort of sketch this out to see this. And 4.2, yeah, that makes sense. That's really close to what I can see on my graph with just sort of a rough sketch. All right, let's go ahead and move forward. We don't need to do that, but that's just kind of something that's useful to do. Make sure our answer makes sense with all the work that we've done previously. All right, what is the first positive value of time at which the point was at the water surface? Okay, so at the water surface would mean that our height above the surface is 0 feet. So we could write an equation where we do this. We do 0 equals 9 cosine pi over 5 x minus 4 plus 7. We could solve this equation. This is definitely an equation we can solve. But because of the specificity, I'm not sure the right word there, of this question, I can't be sure that this is the first time. You know, I don't know. I don't know. This might be the first time when I solve it, but it might not be. It definitely will be some time when we're at 0, because that's the equation we're solving. But there's no guarantee that it's actually the first time. So, and answering whether it was going in or coming out of the water is going to be kind of tricky. We really need to kind of think about that by looking at the graph. So let's go back at our graph and see if we can kind of think about this real quick. So we know the first time it entered the water. Okay. On our graph, the first time it enters or exits water is here. But it might happen over here too. So we have to sort of think about this. So remember, these are about 2.5 seconds. So 1, 2.5 seconds. So we'll be at equilibrium right there. And then 1, 2, no. So we'll be down like right around here. We'll be hitting it again. So this is really, really hard to tell. It might be after we start timing. It might be before we start timing. It's really hard to know if this is happening at a positive value of time, right? It's asking for a positive value of time. It might be positive, but looking here, it actually kind of looks like it might be negative. So we got to be careful here. What we're going to do is look at a more precise graph. We're going to go to Desmos. We're going to create a more precise graph. So let me type this equation in. Y. Oops, I'm just typing in a bunch of y's. Y equals 9 cosine pi over 5 parentheses x minus 4, close everything, plus 7. Okay. And obviously, we need to make some adjustments to our scaling. I'm going to count by ones. I'm going to count by 2 on here, and let's go from, I don't know, -4 to 20. Okay. Want to make sure it's in radians. It does default to radians, but if you change it for some reason, make sure it's there. All right. You could just kind of zoom out until you get there, but it's useful to look at it. All right. So here is our graph. So we were looking for the first time where it was entering or exiting the water, where it was at the water surface. So looking at it, we can see it's actually right there. So that value we're looking at on my graph wasn't very precise. It looked like this might be happening in the negatives, but it's not. It's actually happening right after we started timing. So right after we started timing. So that is the first time. So it was at 0.08 seconds. And then the next question was asking, is it coming in? Was it going into the water or was it coming out of the water? Well, here it's coming out, right? We're on our way up. We're on our way up towards the maximum. So we are coming out of the water just right after we started timing at 0.08 seconds. So that's the answer to our question here. So time equals 0.08 seconds. And we were coming out of the water. We were on our way up towards the maximum after this. So that's kind of going into the explain part. We may want to even provide the graph that we were looking at for that, but there we go. I'm going to go ahead and stop this here, and I'll do the next question in another part. So see you then.